Good morning. This is my second video on the topic waves for JE. In the last video, I discussed the mechanical waves and its types, transverse waves, and longitudinal waves. And I also discussed about the simplest form of the waves, which is simple harmonic waves. In this type of waves, which exist in both transverse and longitudinal waves, medium particles oscillates simple harmonically. So, for the derivation of the equation of waves, I will do a quick revision on the equation of simple harmonic motion. As we know, if I take one example, spring block system, and say this is the equilibrium position of the block, and its amplitude is say upward plus A and down is minus A. It is doing simple harmonic motion about the equilibrium position. Say this position is O. If I project on uniform circular motion, this is the equilibrium position or the mean position, and this I take the positive amplitude upwards, so down will be minus A, negative amplitude, negative side, two extremes, positive and negative. If this block starts oscillating from the mean position, means at t is equal to 0, and say its angular frequency is omega, means is omega. So after time t, it will cover this angle, say theta is equal to omega into t. So its equation, if I take the projection of point P on this, say this is x-axis and this is y-axis. Projection on y-axis, say P dash, then we get OP dash is equal to, say amplitude is A, means radius of this circle is A. This will be A sine omega t. And if we denote OP as y, then y is equal to A sine omega t. If this particle starts simple harmonic motion other than from the mean position, then we may write y is equal to A sine omega t plus phi. Here omega is the angular frequency, A is the amplitude, and phi is the initial phase angle. Initial phase angle at t is equal to 0. Means if this particle starts oscillation from say point, say we take any other point, say this point is Q. So at t is equal to 0, particle is Q. Particle is at Q. Then the initial phase is phi. Then we get the equation y is equal to A sine omega t plus phi. So this equation is the general equation of general equation of simple harmonic motion. Similarly, if the particle starts oscillation, say from the extreme position, then this equation may be written as y is equal to a cos omega t. At t is equal to 0, we get y is equal to a. Y is equal to a. So oscillation starts from the extreme positions. So both the forms, as we have studied, both the form represent the equation of simple harmonic motion. So after this basic knowledge of simple harmonic motion, we'll proceed to simple harmonic waves. So now we'll derive how we can represent mathematically the simple harmonic waves. Say we take one string which is fixed at the one end and the free end is moved vertically up and down, simple harmonically, and say this point is the origin. We take this point is the origin where the source of oscillation is there, and this is the fixed end. So because of this movement of the free end, a wave will be generated or produced. So we want to represent this motion of the wave, which is a moving with velocity v, and the amplitude of this wave is a, and angular frequency is omega. As we have studied, angular frequency and amplitude depends on the source of oscillation, and v depends on the physical property of the medium. We consider any point on the string, say this point is A, which is x distance from the origin. This distance is x. So the wave produced at the origin will reach at point A at a time say t1, and t1 we can represent as distance is x divided by v. So it will take x by v second to reach at point A, so the medium particles oscillating at the origin may be represented as, say, y naught is equal to a is the amplitude of the waves sine omega t. This oscillation will reach at A after time t1. So during this time, the particles at the origin will be ahead with respect to the particles oscillation at A, say by angle phi. So we can write phase at origin, I denote phi naught, this is the phase of the particle, phase of oscillating particle. At origin, and say phi a is the phase of oscillating particle at A. So there will always a phase difference between the two. So this will be phi naught minus phi a. Say this is equal to phi. And this phi we can calculate. Phi is equal to omega is the angular frequency and time is t1. So this phase difference between the particle at origin and at A will be omega into t1. So we can write omega t, we can replace by x by v. This omega we can write 2 pi n. N is the frequency. X v we can write n lambda. V is equal to n lambda. Frequency into wavelength. So this frequency will get cancelled out. We get 2 pi by lambda into x. This is the phase difference. If we replace 2 pi by lambda by k into x, where k is equal to 2 pi by lambda, is called angular wave number. Angular wave number. So now we get phi naught minus phi is equal to phi. So if we replace phi by kx, we get phi a, means phase of the particle at point A, which is x distance from the origin, is equal to phi naught minus phi. And phi naught if you write in terms of omega t minus kx. So we get the phase of the particle at point A as omega naught minus kx. So now we can write the equation of simple harmonic motion of the particles at point A as y is equal to A into sine phi at A is omega t minus kx. So we can write omega t minus kx. This equation we have y shows the amplitude of the particles which is oscillating about the mean position at point A, which is at a distance x from the origin. Omega is the frequency, angular frequency of the wave, and A and omega will remain throughout the oscillations, throughout the propagation of the wave. So A omega is constant. So at any distance x from the origin, this equation gives the amplitude of the oscillating particles. So this is the general equation of wave. General equation of waves, or we can say a progressive wave. Just observe this equation of progressive waves. At x is equal to 0 means at origin. And t is equal to 0. We get y is equal to 0. Means the source of oscillation is at the mean position. If except the mean position, the rest any position if you take, starting from extreme or midway between the mean position and the extreme, we will have a initial phase, just like in case of simple harmonic motion. Y is equal to a sine omega t plus phi. Phi is the initial phase. Same thing we can introduce here also. We get y is equal to a sine omega t minus kx plus phi. So y is equal to a sine omega t minus kx plus phi is the most viable general equation of progressive waves. And things to remember, this we have derived for the propagation of wave in positive x direction. So this represents progressive wave moving positive x direction. If wave is moving to the negative side, if wave moving to negative x direction, then equation of progressive wave will be y is equal to a sine omega t plus kx and plus phi. So just remember, for the mathematical expression and its meaning, if we take negative, it is going positive x direction. If you take the positive sign, that means this wave is moving to the negative side. So we derived a progressive wave propagating in positive x direction with its source located at x is equal to 0, means origin, and it started at t is equal to 0. The equation of motion of particle at position x is given by y is equal to a sine omega t minus kx. Now we'll see the different form of this equation. This is the one form. Second, if we take omega common, we get y is equal to a sine omega, we take common, t minus k by omega into x. And k by omega, if you write, this is 2 pi by lambda, and omega is 2 pi n. 2 pi will get cancelled out. We get 1 by n into lambda, which is equal to 1 by v. This is the speed of the wave. So we can write this equation, y is equal to a sine omega t minus x by v. This is the second form. Another form is, if you take k common from 1, y is equal to a sine, k I am going to take common, this will be omega by k into t minus x. So omega by k, this will be a sine, k we can write 2 pi by lambda. This will be w by omega by k, it's v, vt minus x. This is the third form of the equation. Now we can do this. So we got y is equal to a sine 2 pi by omega vt minus x. Okay. Now the fourth form we can write as y is equal to a sine from this we can write sine, this is 2 pi n t minus 2 pi by lambda into x. So we take 2 pi common, we get y is equal to a sine 2 pi, and we can write 1 by t, so we get t by time period capital T minus x by lambda. This is the fourth form of the progressive wave. So we must remember all four forms of the progressive waves. It will be easier to solve the numericals. So today we have discussed about the equation of waves and its different forms. Next video I will discuss about the expression of velocity acceleration of the medium particles in case of progressive wave. Thank you.